Welcome to the pre-recording of the first half of Lecture 7, scheduled for Wednesday, 26 June in this 8-week summer course. So we are in the middle of the third week. We have introduced greedy algorithms, and today we will see three more greedy algorithms, but now for the same problem. In the previous lecture, we discussed greedy algorithms for three different problems. Now we have three different algorithms for the same problem. In this first half, I will introduce these algorithms and prove their optimality. So a greedy algorithm does something optimal in every step. So in some sense, locally it is an optimum, but that does not guarantee that there is a global optimum. So there is some analysis that needs to be done, and we will be using an exchange argument that we have applied and introduced also last time. In the second half of this lecture, we will discuss implementations, and implementing algorithms in this course means finding the proper data structures to make sure that our algorithms run efficiently, which means that the worst case upper bound on the running time is a polynomial in the input size. Okay, that's kind of the overview. What problems are we now considering? We are considering the computation of a spanning tree. So here is the problem. We have a graph that is undirected. It is connected. That was an implicit assumption for Dijkstra in the previous lecture. It is connected. Every edge has a cost, or in general, it is a weighted graph. The cost is a positive number. We want to compute a subgraph. We call it T. A subgraph, T is actually a selection of the edges of the graph, so that the graph remains connected and that the sum of all the costs is minimal over all possible choices of these subsets of the edge sets. So the brutal force, so I hope the definition is clear. But the brutal force solution would require you to consider all possible subsets for which the set of vertices is still connected. So you still have a connected subgraph of the given graph. You sum up all the sums and you check for which subsets this is minimal. So if you read the definition, you typically always have a brutal force solution. And actually, if we are working on small examples, you can explicitly actually enumerate all the possibilities. Why could we be interested? Well, suppose that you have a certain amount of vertices, nodes in a network to connect. There is a cost to maintain the connections. What is actually now the absolute minimum cost, a lower bound on the cost, if you like, so that the graph remains connected. Here is our running example. We have a graph that is weighted. It is connected. There are 7 vertices and 11 edges. So you can see it's not a fully connected graph, far from it. The number of edges is a little bit more than the number of vertices. So our problem is to find a connected subgraph, start modifying this graph, select certain edges so that the sum of the costs is minimal. And here you can see the sum of the first 11 natural numbers was taken as the costs. So this is a very regular example. Okay, we have a property. So I was using t as the letter, and here also the property uses t of the selection of edges, so that we have a minimal sum. That t, that selection of edges, will actually define a tree. So the main property, it's the title of the slide, the solution of our problem will be a tree. Okay, so what is a tree again? It is a connected graph without cycles. Okay, so if we can prove that the selection of edges so has no cycles, then we are there, because the main constraint on T was that the graph was connected. So the subgraph defined by T is connected. If we show that T has no cycles, then we are done. The idea of the proof is very simple. Suppose there is a cycle, then you can actually remove one of the edges and still maintain connectivity. And since removing a cycle, removing an edge with positive cost, so that's an important restriction. Since removing an edge with positive cost decreases the total cost, it cannot be that a subgraph which is minimal, which has a minimal cost, that subgraph has cycles. So therefore, the assumption that our T had a cycle is false. So the T defines a graph, a graph that is connected without cycles, and therefore it is a tree. Okay, so therefore we can talk about the spanning tree problem, and actually the minimum spanning tree problem. So what is a spanning tree? We already computed the tree of all shortest paths from a given vertex. That was done by Dijkstra's algorithm in the previous lecture. Now, this is also a spanning tree. But we are interested in the minimum spanning tree. So we want that the sum of all the costs of all the edges in this tree is minimum over all possible spanning trees. In the definition, I'm using the letter A. We have the minimum spanning tree problem. It's the problem. And typically we wouldn't talk about the minimum spanning tree. So that's an important distinction here. Okay, so we liked Dijkstra's algorithm, was a good algorithm. Why can't we do this here? Well, the exercise asks you to really prove the statement that Dijkstra would solve the problem. Then this lecture is irrelevant, but it's not the case, so I would strongly suggest you look for a counterexample. Intuitively, Dijkstra's algorithm, the input contains a source vertex. So, and that is kind of restricting. So the example or a counterexample you come up with, you should start with somewhere a graph, and I would say that it can be a very small graph, just a triangle. That will already do it, where the edges to the source have actually a higher cost than the other edges. Or you could also say running Dijkstra with another source would actually do it. But you don't have that option here. Okay, so I think we understand the problem. We also understand the need for algorithms. So now we will give 3 algorithms, 3 greedy algorithms. Here is the first one. It's called Kruskal's algorithm. What Kruskal does, in a nutshell, is adding edges one after the time, starting with the edges that have the smallest cost. Now, of course, you have to be careful. A tree has no cycles. So you will only introduce edges that do not lead to a cycle. Okay, so this is the algorithm. We have our running example, so let's run it. So we have the same input. I have ordered now the edges. The first edge connects vertex 0 to 1. The second edge introduces the vertices 2 and 4. So you see we need to continue because it's not yet connected. Then 5 is connected to 3. That's the third cost. The weights, the costs are kind of chosen in order here. 4 is the cost of the next edge. Then we have 5, and then we have 6. So I should have mentioned that the termination was kind of obvious when I stated the algorithm. Here we can actually be more precise. We actually know that a tree, a connected graph with no cycles, is also any connected graph with n-1 edges on n vertices. So if we have n-1 edges, then we know that we are done. So Kruskal's algorithm will have n-1 steps, as is illustrated here in 6 steps. Okay, that's the first example. The second algorithm is vertex oriented. So you have to make a spanning tree. What you actually do is you choose any vertex. So perhaps what I said earlier was perhaps not that right. So with Dijkstra's algorithm and the source, but it turns out with this algorithm any start vertex will do because you need to connect it anyway. So as long as the selection of vertices does not give the entire vertex set, so we are a connected graph, so this will end. So you can also see that this will take n steps. We will take that vertex that has the smallest attachment cost. So the formula is a little bit complicated. We select that vertex for which there is an edge from a vertex in the selected set. And that edge has actually the smallest cost over all vertices that are not yet selected and that can be connected by one edge to the selected set. Okay, let's see how this algorithm runs. I'm starting here with vertex 0. Why would I not? So then the smallest cost is 1, and that attached 3 or actually over all the vertices that I can attach now, I have two choices. I have 1, and attaching 1 would cost 4, but I better attach vertex 3 that has a lower cost 1. Okay, what is now the next vertex? Well, I can look at attaching 1 that has a cost 4, but I see that 3, and I think that might be, there is 3 to 5, we're just below it. 3 to 5 has a cost 3, and I can better attach 5, which has a lower attachment cost than attaching 1. And indeed, I will attach 5. Okay, Good. So now 4 is probably be the correct answer here. Let me run to it again. Yes, indeed. So which other vertices can I attach? 2 is probably not. Well, 2 is connected to 4, but I haven't 4 yet. So can I connect 4 somewhere? Not via 3, via 1 it is 5, and it turns out that indeed. You can also see one property here is that the attachment cost for every vertex actually is increasing. So the previous attachment cost was 4, now it is 5. So this algorithm has kind of, if you're looking for a lower bound, if the cost is the money you have to pay to connect all these vertices, you can kind of see how far your budget will reach. Next one, 2, and then again, why is what I just said is actually not entirely true. We don't have this increased cost, so life is not as simple. It's the smallest cost over all the vertices that are already attached and reachable by one edge. So here by actually attaching 4 is connected with cost 2 to 2, we actually, the next step is less expensive as a smaller attachment cost. And then we end up with the tree. So here we see the evolution of the Prim's algorithm on our running example. Okay, third algorithm. So there is a third way of doing this. It's called the reverse delete algorithm. So you sort the edges again. So we did this with Kruskal, but now consider we are sorting them in the reverse order. So we are starting by the complete graph and we delete edges. And we keep on doing that as long as the graph is still connected. So we consider all the edges that we can delete and starting with the highest ones. So this is the principle of the reverse delete algorithms. Let us illustrate how that algorithm runs. So we start with our running example. The input is now sorted in order of decreasing cost. So we eliminate the highest cost edge between 5 and 6. 5 and 6 are still both connected. So you can see 10 is the next one, and indeed it's an obvious deletion. 9 is the next one, also quite obvious. Then we have 8. Well, we can delete 8 as well. And 7 is the next one. Are we there yet? Well, in the previous two algorithms, we did 5 steps. So notice that we have 11 edges, we removed 5. So we are left with 6 edges on a graph with 7 vertices. And you can verify, if you do not know this property, then you still have to do a lot of checking. But we know, we have understood the proof and of the characterization property of a tree, that after, if we are left with n minus 1 edges on a graph with n vertices, then we can stop. This is the graph, and here to make the point so that it is a tree. You can redraw this graph, so you can start with vertex 0 as the root, 3 and 1 as the children. So 3 has only one child, that's 5. And you see 1 has only one child, 2, that's 4. 4 has 2 children, 2 and 6. So this is the minimal spanning tree. same tree. Now this is a simple example, and the next exercise asks you to consider an input, a graph, connected, and the three algorithms come up with three different spanning trees. I would suggest to think about graphs where all the edge costs may be the same. So that might give you a hint here on how to find a solution for this problem. Okay, are these algorithms now optimal? So there are three simple algorithms, simple to state, simple to execute, although that's not the reverse delete might be simple to implement because you have to delete. The other ones, we need to do some work on the implementation, but that's the second half of this lecture. So are these algorithms optimal? We will prove first the optimality via properties. So let's look at what is called the cut property. So we look at a graph where all the edge costs are distinct. So the previous exercise, exercise 2, is also kind of an indication that somehow, somewhere, the fact that the edge costs are the same might cause trouble. So all edge costs are distinct. We consider the set of all vertices with the minimum attachment cost. So think about what Prim algorithm was doing. So it's not empty, it's not the entire set, so it's not the trivial cases. Then there is somewhere an edge that attaches a vertex. And that is the minimum cost edge. The property says that we can't really cut that edge because every minimum spanning tree must contain that edge. Okay, we will work by contradiction and using an exchange argument, which was a very powerful argument to prove the optimality of greedy algorithms. So if there would be a minimum spanning tree that does not contain that edge E, the edge with the minimum attachment cost, then we will show that you can exchange that edge for that there is somewhere an edge E prime that you can exchange with E. And so that you have a lower cost. And therefore, the tree that did not have E cannot be a minimum spanning tree. So that's the outline of the proof of this cut property. It's guided by a picture. So here you see the picture. So what did we assume? So the if has our assumption. So E is the minimum cost attachment edge that is not in our tree, which is a minimum spanning tree. Okay, what does that mean? Is that we had this vertex V that was not yet in S. So here actually we have not this edge. So V will be connected, but it should be on the path. It could be directly. It could be that there is a direct path, but in general, we have somewhere another path that runs via V prime. So we can actually swap E prime for E, and you could say, look, indeed, in this assumption, we can still see that V is connected. So V will be connected at via V prime and E prime. Okay, so keep that picture in mind, and perhaps I should, for the slides, switch to the 2-page format. So what do we see? We have now a cycle. So we since the fact that we assumed that E was not in our spanning tree, we can consider adding it. So we have the cycle here. It connects, so swapping removes the cycle, and therefore this T prime that does not contain E is actually a tree. Now we look at the costs. So E is actually the minimum cost between a vertex V and not in the set S and a vertex in the set S. So it's very strict. Now if you were to swap this now, so now you do it differently. Here I crossed out E. If you would now swap E prime for E, you would also have a spanning tree because we have that cycle. You would still be able to reach V prime. So you still have a spanning tree, but now actually you have a minimum cost. So the T prime cannot be a spanning tree. So that is the so the T prime that actually contains E is actually the spanning tree. Okay, the words have it correctly on the slides. I'm sorry if I misspoke a little bit. So there is this picture, the picture proof. You work with the assumption that T does not contain E, but then you can define T prime that does contain E, just by swapping. We have the cycle. So, and with this cycle, we can do the exchange. If we swap in that T, we go to T prime, then actually we have that T prime is still a spanning tree because the V prime can still be reached via V. So we do have T was assumed to be the minimum spanning tree. We have found a T prime that is a spanning tree. Okay. So sorry for the mishap with the erasing. Let's move on. The cut property proves the optimality of Prim's algorithm. So Prim's algorithm stops after n-1 steps and each time attaches new vertices that haven't been attached to this tree. So it's obvious that it is a tree. Is it a minimum spanning tree? Well, yes. So every edge added is actually in every minimum spanning tree by this cut property. So in some sense, the optimality proof is simply a rewording of the technical cut property. Okay, one algorithm is optimal. Let's now look at Kruskal's algorithm. The optimality there can be proven also with the cut property. What does Kruskal actually do? It adds edges without introducing cycles. So we will actually have a tree at the very end. How many edges do you need? n-1. So it also proceeds in n-1 via n-1 additions. So what is it that we are adding? We are adding the minimum cost edge from the cut property. So it contains all the edges that are contained in any minimum spanning tree. So you can't really remove it and still have, or replace it and still have minimality. So we do have a tree, and we have this optimality with the cut property. So therefore we have a minimum spanning tree. Okay, now we are left with one algorithm. That's the reverse delete algorithm. So consider the another property. So again, we are working with graphs where the costs are all distinct. So we assume that there is a cycle. So in that cycle, there is an edge that has the highest cost. So then that edge with the highest cost cannot belong to any minimum spanning tree. So the cycle property is actually the language considering for edges with highest costs. Eliminating edges with the highest costs is something that the reverse delete algorithm does. So in a way, we will prove this property, and that property will lead to the optimality of the reverse delete algorithm. The cycle property kind of mirrors the cut property. If you like, I will be using the very same picture, also using the very same style of proof. Proceeding by contradiction, and we will expose the error in the assumption using an exchange argument. So assume that we do have a cycle, and the highest cost edge is actually still in the minimum spanning tree. Then actually we will show that we can replace in that cycle well, there is no cycle in the tree, but suppose that the minimum spanning tree would contain such an edge that belonged to a cycle of the original graph, then we can replace it with an edge that has lower costs. And in this way, we would find a spanning tree with a lower total cost. Strictly lower, so that's the assumption that we need that all the edge costs are distinct. Then actually we do need, so that assumption is again critical, but the point is that via the swapping, we show the error in the assumption that we had a minimum spanning tree that contained an edge that had the highest cost in a cycle of the original graph. Okay, so I'm using essentially the same picture. So we are now emphasizing things differently. We are starting from the cycle, and we have somewhere an edge sitting there. So we are assuming that E is the edge of in that cycle that has the highest costs. So our assumption, proving by contradiction, started out by saying that we have a spanning tree that contains that edge with the highest cost in the cycle. So I should probably have broken this slide up in several parts. So at the first part we focus on the cycle. But the cycle, the edge connects two vertices, and we have this set S. So in this cycle, so there is we separate the vertex V from the rest from U. And in this cycle, so there is another E prime which has the minimum attachment cost to attach V prime to S. Now, both because we have a cycle, we have this S. Now we can actually now cut E, and if we do that, we can still connect V to the rest of the vertices. So that's the argument. So that will be continued in the next step. So what we do is we are swapping, and perhaps I should do this again in the 2-page argument. We move up. So here we go. So the proof runs from the picture. So in some sense, the four layered 4 slides next to each other gives a complete picture. So we have the statement of the cycle property. You started by drawing the cycle essentially. The cycle contains also the minimum attachment cost. So now we will consider T prime. So T prime contains E prime but not E. So we're exchanging the highest cost edge by the lowest cost edge, the minimum attachment cost. So we are removing only one cycle, so we will maintain a tree. So we have a spanning tree. And because we replaced an edge with a higher cost, we will actually have that T prime has a smaller total cost. So T, which we assumed in the start of the proof, T can actually not be the minimum spanning tree. So T did actually contain that highest cost edge in the cycle. So this proves this cycle property. And that cycle property will lead to the optimality of the reverse delete algorithm. So let's try to prove this. So the optimality, we are deleting edges in order of decreasing cost. So every time an edge is removed, it has the highest cost of all the edges that are still there and that keep it connected. So we are removing essentially cycles. So it must be the most expensive edge on a cycle. So the cycle property does apply. The cycle property says that edges of the highest cost in a cycle cannot be in a minimum spanning tree. So the reverse search algorithm continues until that it can no longer go further. If it would remove one more edge, the graph would not be connected. So it stops when it has all the edges in these cycles removed. So you could also say that it has equivalently removed all the cycles and it obtained a spanning tree. Okay, so we have thus removed all the expensive edges and we obtained a tree. So it has no cycles, it's connected, it is a tree. So this proves the optimality of the reverse delete algorithm. Okay, I hope that this was not too confusing. So the assumption that all edge costs are distinct was critical to prove the optimality. So then the algorithms are not optimal if the edges all have the same costs. Well, actually, you could do a trick. You could add infinitesimally small costs. If you are familiar with numerical analysis, or you should know the notion of machine precision, you pick numbers that are floating point numbers here. So this is an course on discrete algorithms, but you can sometimes cheat. And these are imaginary numbers, by the way. So if you add them to the costs, if you work with floating point arithmetic, you don't really notice. So they are less than the machine precision. So you use these epsilons to uniquely order all your edges. So you can still actually break the ties. This observation may be some cheap trick, but it will also help you with the second exercise. So regarding the uniqueness of the minimum spanning tree. Okay, one last exercise. So in the second half of this pre-recording, we will consider the implementations of Prim and Kruskal. As an exercise, we leave the implementation of the reverse delete algorithm. In some sense, while we were running through our example, it might have seemed that the reverse delete might have been easiest. You just remove things, so you just wiped things out. Doing things by hand and doing things on a computer is different, so it's not necessarily so that that is the best way to go. So which data structure should you choose now? Justify your choice. And remember our edge presentation, our graph representations, adjacency matrix or adjacency lists. Our running example was probably a typical graph with not that many more edges than you have vertices, but you can already see that with the reverse delete, you will have to delete a lot of edges if you have a fully connected graph. So for a graph with m edges and vertices, what is the worst case running bound? So you will have to consider all the edges actually. Also, but now if you justify your bound, you are deleting edges. You have to make sure that in your data structure you can delete the edges with a constant cost. So that is important in solving this exercise. Okay, I'm close to 45 minutes, which is kind of the budgeted time. So we will continue in the next pre-recording, the second half of this lecture on data structures to implement Kruskal, and then we will review priority queues needed to implement Prim's algorithm.